Hey, you know those incredibly intelligent AI language models we hear so much about? Get this. Some of the really advanced ones are so massive in their digital size that they can't even fit onto the most powerful gaming graphics cards out there.
Wow, really?
Yeah, think about that for a second. The cutting edge of AI is already bumping up against the limits of even high-end hardware just to exist. Have you ever wondered how these behemoths actually get used in everyday applications? That's the puzzle we're diving into today.
It's a really important puzzle, too.
Definitely. We've been digging into the latest research on how to shrink these powerful AI brains down to a more manageable size without, losing their smarts.
And you, our listeners, you're all about getting the real story quickly and understanding why it matters, right?
Yeah.
Without getting lost in a maze of technical details.
Exactly. That's exactly what we're aiming for.
What's truly fascinating here is that this sheer size isn't just a tech spec. It creates real-world bottlenecks. You, our listener, have likely interacted with these impressive models.
Oh, for sure.
But have you paused to consider the logistical challenge of deploying something so computationally demanding on, like, regular devices? Or even cloud infrastructure that isn't, a supercomputer? It's a significant hurdle to making this technology truly accessible.
Exactly. It's like trying to pack a stadium into a suitcase. You need some serious innovation in how you fold things up.
Yeah, good analogy.
And that's where our deep dive begins. We're exploring how researchers are tackling this head-on, making these incredibly capable language models smaller, faster, and, more efficient. Our focus today is primarily on a really interesting piece of research titled Mixture Compressor for Mixture of Experts LMS Gains More. This paper introduces a brand new way to dramatically reduce the size of a specific kind of advanced language model.
And our mission for this deep dive is to understand the magic behind this mixture compressor, or MC as it's called. It's designed to compress a particular type of large language model known as a mixture of experts, or MoE LLM. We want to unravel how MC achieves this extreme compression and what that means for making these powerful tools more practical in our daily lives. So, let's get into it.
Okay. So to really appreciate why Mixture Compressor is, a big deal, we should probably first understand what makes these Mixture of Experts models different.
Good idea.
You see, most large language models are kind of like a single giant brain trying to process everything. But MoE models are structured more like a team of specialists.
Okay.
Imagine you have experts in different fields, say history, science, and literature. When a question comes in, a kind of traffic controller decides which of these experts is best suited to handle which part of the question.
Right.
Only those relevant experts get to work, which can make the whole process much more efficient.
That's a great analogy. This selective activation of experts is what makes MoE models potentially very powerful and fast. However, the research paper we're looking at points out a couple of key challenges. Even though only a fraction of the experts are active for any given input, the entire team, and these teams can be quite large, needs to be ready and waiting in the computer's memory. This leads to enormous memory requirements and, slow loading times. Think of it. Even if only 3 specialists are consulted, you still need the entire department building ready to go.
Right, so even if they're not all working at once, they're all taking up space. The paper mentions that even a top-tier NVIDIA A100 graphics card with the massive 80 GB of memory can struggle to hold some of the larger MoE models like Mistral 8x7b.
Yeah, that's huge.
In their fully uncompressed state.
Yeah.
That's a pretty significant roadblock to using them widely.
Definitely.
The second issue they found is that the experts who are activated can sometimes be a bit redundant.
Redundant? How so?
Well, it turns out that for many of the basic units of language, called tokens, the model might only really need the input from a single expert, even though it often activates 2 or more.
Exactly. It's like calling in 3 plumbers when one could easily fix the leaky faucet.
Yeah.
So these models are incredibly smart, but they're also bulky and sometimes a bit inefficient in how they use their internal expertise. This is the problem that Mixture Compressor aims to solve. The researchers made 2 crucial observations that paved the way for this technique. What were those key insights?
Okay, so the first thing they noticed was that not all the experts within a MoE model contribute equally.
Right. Some are more important than others.
Exactly. They found that different experts behave differently in several important ways. For instance, they have different levels of how much information is lost if that expert is somehow altered or removed. They call this activation reconstruction error.
Okay.
They also have different routing scores, which tell us how often and how strongly they are chosen to handle different parts of the input. And simply, they have different activated frequencies, meaning some experts just get called upon much more often than others. This all pointed to the fact that some experts are far more vital to the model's overall performance than others. It's like on our expert team, some players are the star performers, consistently making key contributions.
Precisely. Some experts are the go-to authorities, while others play more niche roles. The second key observation was about the input itself.
The input text.
Yeah. They realized that not all tokens or parts of the text you feed into the model are equally important for the model to understand and generate a relevant response. It turns out that only a small fraction of the tokens might be absolutely critical for the model to grasp the meaning. This suggests that the model might be spending valuable computational resources on processing less significant parts of the input.
Right.
Think of it like reading a sentence. Some words carry the core meaning, while others are more like supporting details.
Okay, so we've got this imbalance. Some experts are more crucial than others, and some parts of the input are more important than others. How does Mixture Compressor take advantage of this to achieve such, significant compression?
This leads us to the two main stages of MC. The first is preloading mixed precision quantization, or PMQ.
PMQ. Got it.
This is a process that happens before you even start using the model to generate text. The core idea is to reduce the amount of storage space and the time it takes to load the model into memory by using lower precision, fewer bits to represent the less important experts.
Fewer bits.
Think of it like storing music files. A high-quality file takes up more space than a lower-quality one, but you might not notice the difference on regular speakers, right?
Right, yeah.
PMQ does something similar with the numbers inside the AI model.
That makes sense. But how does it decide which experts get the lower bit treatment? You can't just randomly reduce the precision of some parts, right?
Yeah.
Wouldn't that mess things up?
Exactly. You can't just do it randomly. This is where their first key observation comes into play, and it's quite clever. PMQ formulates the decision of how many bits of precision to give to each expert as a mathematical problem called linear programming.
Linear programming.
Okay. Imagine trying to create the best possible recipe using a limited amount of different ingredients, where each ingredient contributes differently to the final flavor. Linear programming helps find the optimal balance.
Okay, I think I follow.
In the case of MC, the ingredients are the different levels of precision for each expert, and the goal is to maximize the overall performance of the model while staying within a budget of total bits.
A bit budget. I like that.
Yeah. It considers how often an expert is used, how important its contributions are, and the potential loss in accuracy if that specific expert is compressed too much. It's a very smart way of allocating resources.
So it's a sophisticated way of deciding who gets to be represented with high fidelity and who can be represented with, well, a bit less detail without sacrificing too much overall quality.
Precisely.
Now, what about the second part? Online dynamic pruning, or ODP. That sounds like it happens while the model is actually running and generating text?
That's right. ODP kicks in during the inference phase, when the model is actively processing input and generating output. It builds on the second key observation about the varying importance of tokens.
Right, the important words versus the less important ones.
Exactly. ODP tries to identify which parts of the input text are the most critical and ensures that the model focuses its computational power on those. For the less critical parts, ODP can dynamically choose to use fewer of the activated experts.
Wow.
Essentially skipping some computations that might not be necessary. It's like if you're reading a complex document, you might spend more time and mental energy on the key paragraphs and skim over the less important ones.
So the model is learning on the fly which parts of the input really matter and then streamlining its processing for the less crucial bits. How does it figure out which tokens are important and which experts can be skipped for those less important tokens?
Well, the paper explains that they have a strategy to identify and protect these important tokens. They look at how much different parts of the input are influencing each other. This is captured by attention scores.
Attention scores, okay.
They also look at the internal representation of each token within the model, its feature magnitude. By considering both of these, they can pinpoint the tokens that are most influential for the model's understanding.
Makes sense.
For the dynamic expert selection, they examine the routing weights assigned to each expert for a given token. If an expert has a significantly lower routing weight compared to the others for a particular token, it suggests that this expert isn't very confident in its ability to process that specific part of the input,
Yeah.
so it can potentially be skipped, saving computational resources.
That sounds like a really ingenious way to speed things up without losing the core understanding.
Yeah.
So what kind of results did the researchers achieve with this mixture compressor technique? Did they actually manage to shrink these massive models down to a more reasonable size?
Oh, yeah. The results were quite remarkable. In their experiments, MC achieved a very high level of compression. For instance, by reducing the average number of bits used to represent each parameter in the model to just 2.54.
2.54 bits, wow.
They achieved a compression rate of 76.6%.
76%.
And perhaps even more impressively, the loss in accuracy on a set of 8 common-sense reasoning benchmarks was surprisingly small, averaging only around 3.8%.
Only 3.8% accuracy loss. That's tiny for that much compression.
It really is. That's a huge reduction in size with a minimal impact on performance.
Wow, a 76.6% reduction in size with barely a scratch in accuracy. That's the kind of shrinking we were hoping for. But did this compression translate into tangible benefits, like being able to run these models on less powerful hardware or making them generate text faster?
Absolutely. The paper highlights a particularly striking finding. They demonstrated that a compressed MoE LLM using MC, specifically a version of Mistral 8x7b, compressed down to just 2.54 bits.
The same one?
Yeah, that one actually performed better on a key benchmark called MMLU than a much larger uncompressed regular language model, LMA213b.
Better. The smaller compressed one performed better.
Better. And it did so while being significantly smaller. That really challenges the idea that bigger is always better when it comes to AI models.
That's incredible.
Yeah.
The compressed version outperforming the original larger one in some cases.
Yeah.
So it seems efficiency can sometimes trump sheer size.
Oh, this certainly suggests that.
What about the speed? Did MC also lead to faster processing?
Yes, it did significantly. The online dynamic pruning component of MC directly contributes to faster inference, which is the speed at which the model generates text.
Right, inference speed.
Their experiments showed speedups of up to 1.80 times compared to the original uncompressed model.
Wow, almost twice as fast.
Yeah, that's a substantial improvement in how quickly these models can respond.
So, okay, to sum up, we're talking about making these incredibly powerful language models dramatically smaller.
Yep.
Allowing them to perform just as well, if not better, than their larger counterparts in some situations,
Yeah.
and enabling them to generate text much faster. This sounds like a major step forward for making this technology more practical and accessible.
Precisely. By making these highly capable AI models more efficient, it opens up a wide range of possibilities for deploying them on more readily available hardware. This could lead to innovations in various applications and devices that previously lacked the computational power to handle such sophisticated models.
Okay, let's boil down the key takeaways for you listening.
Good idea. Bullet points.
Yeah, let's do bullets. First, MoE language models are very powerful but require a lot of memory and can be slow to run. That's the basic problem.
Right. And the Mixture Compressor, MC, technique addresses this through 2 main steps: that preloading mixed precision quantization, PMQ, and the online dynamic pruning, ODP.
PMQ cleverly reduces the size of different expert components, assigning more bits, more precision to the most important experts and less to the less critical ones. And it uses that smart linear programming thing to figure out the best balance.
And then ODP speeds things up during operation. It finds the most important parts of the input and focuses the model's computations there, letting it skip some processing on less crucial parts for other input, protecting those important tokens.
And the results. MC achieves impressive compression like that 76.6% size reduction down to an average of 2.54 bits per parameter.
With minimal loss in accuracy, only around 3.8% on average across standard tests, which is amazing.
And remarkably, a compressed MoE model using NC can sometimes even outperform larger, uncompressed regular language models, like that compressed Mistral beating the bigger LMA2.
Plus, MC leads to significant speed improvements up to 1.80 times faster inference in their tests.
So ultimately, this makes it much more feasible to run these really powerful language models on more common and accessible technology.
Exactly. Which leads us to a really interesting question for you to ponder.
Ooh, a thought provoker.
Yeah, consider the implications of being able to deploy the power of these massive AI models on everyday devices. What entirely new applications and innovations might we see emerge when these tools are no longer confined to massive data centers and specialized computing infrastructure? It really opens up a world of possibilities and makes you think about how this kind of computational power could become truly ubiquitous. What happens when your phone or your watch or maybe even your fridge has that kind of intelligence built in?
That's a fascinating thought. What does become possible then?
Uh-huh.
Definitely something to mull over.